Good afternoon.
Good afternoon.
All right, we have a couple examples from chapter 5 to do first. So we'll start with 5.15. Carbon steel, AISI 1010, shaft of 0.1 meter diameter, heat treated in a gas-fired furnace whose gases are at 1200 Kelvin and provide a convection coefficient of 100 watts per meter squared Kelvin. If the shafts enter the furnace at 300 Kelvin, how long must they remain in the furnace to achieve a centerline temperature of 800 Kelvin? All right, so we have carbon steel shaft. It's AISI 1010. The diameter is 0.1 meter. We have T infinity equal to 1200 Kelvin. Convection coefficient is 100 watts per meter squared Kelvin. Okay. We have an initial temperature of 300 Kelvin, a centerline temperature that it's asking for of 800 Kelvin, and then they want us to find how long must they remain in the furnace to achieve a centerline temperature of 800 Kelvin. So we have how long, right? All right, so we're looking for a delta T, okay? All right, the schematic. All right, so we have our shaft here. There's around it T infinity and H, okay? We have a diameter okay. Okay. So where do we start? Any ideas? So we have this steel shaft, right? Heat treated in a gas furnace. The gases are 1200 Kelvin. We have a convection coefficient. These shafts enter the furnace at 300 Kelvin. And then after some amount of time, the centerline temperature becomes 800 Kelvin. Okay. So, and they want us to figure out how long it takes.
See the energy or the equation.
Which equation? Sorry.
To find the dt.
Okay, the energy equation?
Yeah, sorry.
Okay, that's all right. So if we looked at the COE, right? Okay. And what energy do we have forms of going in or out? And our boundary, let's first off do our boundary here. We're going to do around the whole thing, right? All right, so what types of heat transfer do we have crossing our boundary? What kind of energy in, energy out? Do we have energy generated?
Convection.
So we see we just have convection given to us, right? So we're neglecting radiation. And we actually only have a convection only problem, right? We don't have an applied heat flux that was given or an energy generated term, right, given. So it's a convection only, right? So this looks like this, okay? And we can integrate this, okay? And that's where, if we look at our chapter 5, we basically took our equation that you see here, and we only have this term, and we have this term, okay? So that's convection only, right? So here's just negligible radiation. So we could have done this and just set energy generated to 0 and this to 0. Or we can do the case where we just have convection, energy generated 0, surface heat flux 0. So we have our equation that we just did, right? And if we do our substitutions, we can integrate and get this one right here. Okay, so that gets us okay, so we have this version, or if we wanted to do the one with the time constant, just looks like this, okay, where the time constant is just this, okay? It's just inverting that, all those constants together. All right, so we did this, we saw convection only. What do we first off, to even do this, we're basically saying we have 1D convection and 1D convection radial direction, right? And constant properties. Okay. We also said it's an isothermal shaft. Okay, so that the temperature is always the same inside to do this. Like at any given temperature throughout the whole shaft is the same temperature. All right, so if we look at this, right, we are trying to solve for how long, okay? We got to see what we were given, right? We were given convection coefficient, right? So either way there. And we were given T infinity, right? T initial. So we need that temperature, right? We need specific heat, density, and we need our surface area over volume, okay? And then time, okay? So how do we get, let's start with do we have the temperature? Let's do that.
Is that the center line temperature?
Yeah, so that's the center line temperature. So T is equal to T center. Since we're saying that it's isothermal, right, it's the same temperature throughout at any given time, okay, then the temperature at the center is the same as the temperature at the surface, okay? So it's one temperature, okay? All right, so we have that. What about the properties? Say density, specific heat in the equation. Where do we get that?
From the table.
Yeah, so the tables, okay? So we were given something nice and specific. They gave us AISI 1010, right? So AISI 1010, and we can go to our appendix. And that's going to be table 8.1. And we're going to just basically take a T average, which is 550 Kelvin, okay? Because it's initially at 300, and then after some time, it's 800. So we're just averaging it together because, you know, it's going to change. Properties are going to change with time, but we're saying constant properties. So to bring back some of that lost accuracy, because the properties do change with time in this case, it's, you know, they don't change that much. We're just going to take them at the average temperature. Okay, and that's 550. Okay, so we go and grab those different properties. We see densities 7832. Thermal conductivity is 51.2. The specific heat is 541. Thermal diffusivity 1.21. Okay, so we have a whole bunch of properties we can grab, and we see that has density, that has specific heat. Okay. Okay, so then we're left with the surface area divided by volume. Okay. And this is a cylinder, right? So surface area, we have pi CL. Volume, we have pi over 4 d squared L. Okay. So if we look at that, oh, I made capital D and then lowercase. All right. Pi. All right, so then we look at that, we see this is 4 divided by diameter, which is the same as 2 divided by radius. Okay. So we have diameter. Right? All right, so if we plug this all in, that means we got everything, and we can just solve for time. So we get a time of 8:59 seconds. Any questions? Are we missing anything here?
Do we need to do the buyout numbers?
Yes, we do. All right. We assume some things in this. These assumptions mean we need to check. Right. We said isothermal shaft. Right. This is where we're check the buyout number. Okay. We made an assumption, and we started basically right here. We used the lump capacitance method. Right. And the lump capacitance method basically is assuming an isothermal shaft at any given time, which means we need to check the buyout number because the lump capacitance method is valid only at certain buyout numbers. Okay. All right, so the buyout number is H characteristic length over thermal conductivity of the solid. Okay, so in this case of the steel. Okay. Which this is, as we saw in our slides in our lecture, is a ratio of resistance from conduction over the resistance of convection. Right? It's basically seeing which is, more dominating, or is it, very fast conduction relative to convection, so that we can assume it's isothermal inside the shaft. So any heat that gets put into the shaft, it equalizes and gives basically the same temperature throughout the shaft in the radial direction. All right, so if we look at this, we have H, and we got the thermal conductivity of the solid, right, of the steel. So then we need the characteristic length. And that just ends up being volume divided by the surface area. Okay, and we actually just did that above, right? That is just diameter divided by 4, or radius divided by 2. So in the chapter, they actually have a few of characteristic lengths. They'll have it on page 259, first paragraph. where they talk about basically give the characteristic lengths for a long cylinder, sphere, and a plane wall. Okay, we already just calculated the one for a long sphere, or sorry, long cylinder. Okay. Any questions so far? All right, so then we now have enough to solve for the Biot number, so we get a Biot number of 0.0488, right? And so what did we use in the slides or in our lecture as our kind of criteria for our Biot number?
Less than one. Much less than one.
Much less than one, right? So that's where much less than one. So we'll just use for checking with an exact value of less than 0.1, okay? So in that case, we're good, okay? So we can use the lump capacitance method. All right, if we wanted to check this, just for there's an exact solution in the section we skipped over, okay? So I'm just showing this for comparison's sake. So exact solution, we have basically equation 5.52C. If we use that, we get a time of 9:15 seconds, which is, 6% air we saw, then air above. Okay, and a lump capacitance. And that's because we're, basically 0.05, which is half of that 0.1. Okay, and as we get closer to that 0.1, that air becomes bigger. As we get lower and lower in the Biot number, that air becomes smaller and smaller. Okay. So, and the air is basically talking about the influence of that the temperature changes in the radial direction too. So it's talking about this temperature change kind of in the radial direction, that we can't just assume it is one temperature, because that temperature is also influenced by the radial heat conduction, not just time. So not just time is the influence, but also radial. So it has those two dependencies. And if we include those, which is that exact solution part, you get a little bit more accurate number. Okay. Any questions? Okay. So if we then do another problem, let us do 5.26. Before being injected into a furnace, pulverized coal is preheated by passing it through a cylindrical tube whose surface is maintained at 1000 degrees Celsius. The coal pellets are suspended in an airflow and are known to move with a speed of 3 meters per second. If the pellets may be approximated as spheres of 1 millimeter diameter, and it may be assumed that they are heated by radiation transfer from the tube surface, how long must the tube be to heat coal entering at 25 degrees Celsius to a temperature of 600 degrees Celsius? Is the use of lump capacitance method justified? Okay. All right, so we have pulverized coal. Okay, the surroundings are at 1,000. One more zero. Degrees Celsius. The velocity is 3 meters per second. The diameter is 1 millimeter, which is 0.001 meter. It says there's radiation heat transfer. Okay. It says the initial temperature is 25 degrees Celsius. And then at the end of this tube, the temperature is 600 degrees Celsius. They want us to find how long must the tube be? And then is lump capacitance justified? Okay, so we have our schematic. So we have our tube. There's our X direction, and then we have over here is where it's a length of L. We have our coal particle right there, our coal pellet. All right, and we have this air flowing through, or the pellets flowing through, let's say, basically. So it has a velocity. And the surface is 1,000. Okay. And we have TL. And then right here is our T initial. Okay. Okay. So we have this coal particle moving along this tube furnace that has a velocity of 3 meters per second. Surrounding the walls of the surroundings are 1,000. It says radiation heat transfer. Initially, it comes in at 25 degrees Celsius. It exits at 600, but they want us to figure out how long must this tube be to do that, right? So let's change that. Will be a length L we're basically looking for. So where do we begin? Where do we start? What types of heat transfer are going on, right? Where do we begin?
Radiation.
So we got radiation. Okay, and
Probably convection from the airflow.
so yes, so there could be convection in this, but in this problem we're actually going to be neglecting it. Okay, so they are basically telling us it's it didn't say radiation only, but it's heated by radiation is what they're saying. So that is kind of saying radiation only. Okay, but we could always check this if we knew the convection coefficient, or later on we can solve for the convection coefficient in a problem like this. So we're really going to be neglecting convection.
And is the fact that they didn't give you a coefficient and that coupled with saying heated by radiation, is that kind of a
yeah,
way
that's
of them
kind of
saying,
the gimme in the book
Okay.
problem. Yeah, in a practical problem, you could do a calculation of looking at, well, this one. Let's say you had a version that looks like this for radiation. Okay, so we have radiation and we have convection, right? And you could, should be parentheses, calculate, what is this heat, right, from convection? What is this heat from radiation? Okay, so then which one, and you could just, do it at the initial temperature, do it at the final temperature, or do it at an average temperature, and kind of get a rough idea of what would be the dominating heat transfer, or are they the same order of magnitude, right? If you do that kind of rough calculation of, initial condition and then at TL, which is dominating, or are they at the same level? Then you got to include convection and radiation, okay? And that's more the practical sense of what you do for a problem. In the sense of these book problems, they're more, so straightforward, and they give you exactly what you kind of really need, right? And they didn't give us convection, so, we get to neglect it.
Okay.
Yep. All right, so we're neglecting convection, radiation, and there's no surface heat flux. Is there any energy generated? No, they didn't give us that either, right? It wasn't a given on that there's any applied surface heat flux at the same. There's just, they gave us radiation, right? There's no energy generated that was given, but I'm going to say neglected in this case for the energy generated. Because this is coal and it's going up to 600 degrees Celsius. So there could have been some chemical reactions going on if this is air that's surrounding it. So we're neglecting anything dealing with that. Yeah, so I wanted to make sure we say something like that, call it out. All right, so we have radiation only, right? Again, we have 1D conduction, constant. Properties. Now what? Now where do we go? We know we've simplified it to radiation only. Now what?
Use that radiation only equation.
Yeah, so we're basically conservation of energy. We're applying the radiation only, which means we're applying capacitance, right? Which is the isothermal. So that's telling us check by it number, right? And for doing that, we neglected convection, heat flux, no energy generated. So all we have is this term and this one, right? So if we do that, that's not this one, that's this one. That's basically just those two terms, okay? And if we integrate it, we have this nice small equation, right? Okay. So I'm a glutton for punishment, so let's write it out. Let's make it better. I guess that'll do. All right.
Professor, shouldn't you have the emissivity in the denominator as well?
Okay. Yes. Thank you. All right, so let's go through. We were given temperature of the surroundings. Okay, temperatures, right? Let's start off with that. We are doing radiation. We definitely need to change all these into Kelvin. Otherwise, we're going to get the incorrect answer. There's a lot of, dividing, in the radiation only. Radiation has that to the fourth, right? So that's why it always has to kind of be in that Kelvin. And you see it here with the division kind of here with the TI over T surroundings and T over T surroundings. And then surroundings temperature divided by, or cubed right here. Okay. So we have T surroundings. We have T initial. And what's our T?
$600 or the 873. If you, but you would have to assume it's isothermal.
Yep. So the temperature is the temperature at TL, which is our 873 Kelvin. So we said lump capacitance, which assumes isothermal. Okay. All right. So then let's look what else. This is a constant. This is a constant. All right. So then let's see what we don't have. We need density, volume divided by surface area, specific heat, emissivity. Okay. Am I missing anything? No. All right, let's start with density and specific heat. We can do like we did in the last problem, right? We have coal, right? So in table A3, we have properties, and we take again T average, which is 585 Kelvin. Okay, so that gives us a density of 1350 kilograms per meters cubed. Specific heat of 1260, and a thermal conductivity. All right, so if we do that, that means we have the specific heat, we have density. So now we have left is emissivity and volume over surface area. Well, the back of the book for emissivity isn't there for coal, so we're gonna have to make an assumption, okay? So the emissivity, we're gonna assume it's equal to 1, okay? So we have that. So then we need volume over surface area. And it's a sphere, okay? So if we go to our table, that paragraph, I should say, that I pointed out in the last problem, and basically it's just putting in the volume of the sphere, surface area of the sphere, and reducing it. We're gonna get that diameter divided by 6 is volume divided by the surface area. So we have diameter. So that means we have everything to solve for time. So in this case, we have a time of 1.18 seconds. All right, so, but we're trying to figure out how long the tube must be, not the time. So what do we got to do here?
Use the velocity to figure out the thing.
Yeah, so the velocity is staying constant. It's 3 meters per second. All right, and if it's at 3 meters per second for 1.18 seconds, we can just have our length be velocity times time. So we get 3.3 .54 meters is how long this tube furnace needs to be to get this coal pellet from 25 degrees Celsius to 600 degrees Celsius at the end. Okay, so that's the length. And then, is lumped capacitance justified? What do we got to do for that?
The buyout number.
Yeah, so we got to look at our buyout number. So characteristic length, volume over surface area, and we already did that one. Okay, so we have that. We have thermal conductivity of the solid, which is the coal. So we need the convection coefficient, right? But we said there is no convection, right? Just radiation. So what do we do for this?
Is it 0?
No. We have to find an equivalent one. Okay. So because Biot number is just the resistance of, the conduction over convection. So in this case, there's no convection, but so then it would be the resistance of conduction over the resistance of radiation. Okay. So to get this H value, we actually need to get the equivalent kind of HR, convection coefficient, what a convection coefficient would look like for this radiation condition. And that comes from way back in chapter 1. We saw something that looks like this. So this is equation 1.9. Okay. All right, so if we look at that one, we have surrounding temperature, emissivity of 1, Stefan Boltzmann's constant. Then we just need temperature of the surface. What temperature do we use then? For the temperature of the surface?
Would it be the 873?
So at the exit, okay. So if we say the temperature of the surface is TL, which is 873 Kelvin, and we calculate our radiation convection coefficient, or radiation coefficient, right? And from that, solve for our Biot number. We're going to get a Biot number of 0.19 in this case. Okay, and that's going to tell us what?
Not applicable.
Yeah, not applicable or let's say limited accuracy, let's say. So this might be more of a ballpark number. a rough estimate, right? Or we can also check it if we were to take the initial as the surface temperature, because it's initially at the beginning of the tube furnace, it's 25. At the end, it's this 298 initially, and at the end, it's 873 Kelvin. So if we did it then at the beginning and calculated the Biot number when it first enters the furnace, it's at 0.1. Okay. So even here, it's kind of right on the limit. Okay. So we see, it's close, right on the limit. Right here, and then it's, going above it as it works its way through. And so that's basically saying, like I said, it's a ballpark number. So maybe you just need a ballpark number on this furnace, and you're not trying to get it to be exactly 600, maybe just kind of near it. Then this might be enough for you. But if you needed more accuracy, then you might want to go into one that accounts for that temperature change in the radial direction inside the sphere, along with the temperature change due to time. So it takes into that influence of both time and radial direction. Which would be the other sections we skipped, or numerical analysis within, NX or something like that. Questions? All right, so then we have this exam